All right, having just discussed how an IP address is like a building location where you have a general region and then a particular spot within that region, let's carry on and talk more about specifics and facts related to IP addresses. Okay, so for each device within a particular network, it needs to have a full IP address associated with it, and then each IP address participates or is a member within a particular network that's associated with a network address. So there's a network address that represents the overall network within which or subnetwork within which an IP address, a particular IP address, is going to be found. Okay, so let's build some more conceptual ideas here. Here's a question. How many network addresses are needed for this internetwork? So pause and think and count that for a second. Okay, hopefully what you found was 10. So the hard part, or the part that's easy to miss, is that we need an IP address associated with each interface on a router that connects to a particular network. So over here on the left-hand side, 1, 2, 3, we have our devices, or our computers or phones, that sort of thing. But then the fourth IP address over here gets assigned to the router. And then on the other side of the router, there's going to be another network over here with its own unique network address. And so for every network that it connects, for every device on the network that touches the network, it needs its own unique IP address. Here is a different question. How many networks are needed in this internetwork? Pause and think about that and see if you can determine that. Okay, you can see that there are 4 here. So over here you have network 1, which is on one side of the router. We have a different network, which is between these two. A different network over here, network 3, which is on this side of the router, and between this router and probably the internet, we have another network. And so just to be more specific about that, let me jump back to this previous picture where over here on the right-hand side, on any side of the router, we have the name of the network that's associated with it. So we have 3 different networks, and then we have a number of devices associated with it. And any connection between routers has a network associated with it that's a different network. It doesn't have to be completely different class A, B, C network differences. It can be just a different subnetwork within a given IP address space. But this gives you the high-level idea. Okay, so more about IP addresses. If you've messed with Windows very much and set static IP addresses, you've seen something like this little window here on the right-hand side. And in the first row of boxes, you'll fill in your IP address. And in the second, which hopefully makes a lot of sense now. And then the second row is where we fill in something called a subnet mask, which is something that we haven't discussed a lot before. So the first row is a 32-bit number, so it's 4 numbers that are each represented by 0 to 255, so 4 bytes essentially. And here's some examples of what an IP address could look like. We could represent it by 4 decimal numbers. We could alternatively represent that in hexadecimal, or we could represent it in binary. So here we have our 32 bits, or 4 bytes, if you will. But then we have this other number that we haven't talked about much before, which is very important, and it's called the subnet mask. And it's similar in that we have 4 8-bit numbers, or again 32 bits. But usually you won't see as much variation in the numbers in any particular slot. And there's that you see here compared to an IP address. And there's a very good reason for that. But in this particular case, it looks similar to an IP address. It's a number that appears to be between 0 and 255. It can also be represented in hex, and it can also be represented in binary. And then there's something else related to representing our IP addresses. Instead of then this will come up quite a bit, and you'll need to be familiar with it. Although we can sometimes fill out that first and second box, we can also represent it shorthand like this. So the first part of it we've seen before, that's our IP address. But what about this second part? This is called CIDR notation. And what this means is that if we were to create our subnet mask, that it would be represented by 24 uninterrupted ones. This could be anything. It could be a 12. It could be, well, anything between 0 and 32. Anyway, but whatever number that is that's there, that means just how many ones are going to be represented before it becomes zeros. So if this was /25, then we would have another 1 right there if we were to turn it to binary. And this is going to have important implications later on. All right, so why in the world do we have this second row? Well, one of the reasons for this is we need to subdivide our networks. So previously, I've talked about how within a private address space you can have lots of different variations of numbers here, and in total you can have millions of different devices that are all within the exact same network, that are all within communicating with one another simultaneously, and that can really burden a network in terms of the bandwidth and taking it down. If you're on a floor of let's just say you have a big company and you've got 8 floors or something like that in your office building, like why not put every floor on its own network? Why does every single device need to see every other device in the building? And most of the time it doesn't make sense. So for one reason is to preserve our bandwidth and not have our computers chattering with one another all the time, just needlessly finding out who's there, I'm here. What we can do is we can subdivide our networks and use this space more intelligently. So rather than having one network, maybe we could have several hundred networks, each with a relatively small number of hosts within each one, and their traffic is not all competing with the other ones. So that's what a subnet is for, is to more intelligently subdivide our networks. Okay, and here is how you can conceive of or think about a subnet mask, or just any IP address that's representative of both the original address and the subnet mask. So at the top here we have an address that's represented both in its decimal form as well as in binary, and then on this lower one we have this particular subnet mask represented in binary. And where the numbers run out in the subnet mask, regardless of how you do this, sometimes we don't have a 0 here, sometimes we have other numbers, which means our 1s are going to go out a couple more, but wherever the 1s run out, we can draw an imaginary line, and anything to the left of that line is going to be considered the network ID. So remember, as we looked at our spaces, we have a network, or a general region that we're in, and then we have the individual addresses. So coming back over here again, anything to the left of the 1s in the subnet mask represent the network, and anything to the right of the 1s, which are going to be all 0s in a subnet mask, are going to be available for assigning an IP address. So these extra digits right here allow us to create the number 66, but technically, if we assigned this 00, the network that's going to be associated here is 207.173.75.0. That's going to be, in this particular case, and hopefully it'll become clear why in the future, if we set this all to zeros right here, based on this original IP address, if we set this all to zeros, then this 75.0 is going to be the network space that we're in. And if we set this all to 1, that's going to be, we'll be able to create the number 255. And just the way this works is this particular IP address with this subnet mask is bound between, if this were all 0s and all 1s as numbers. And so if this were all zeros, this would become a 0. 75.0 is the low end of the range of our addresses, and technically that's called the broadcast address. It's not assignable to hosts. And on the upper end, we get 255, if this were all ones, and that's the broadcast address that's not assignable. But everything between 0 and 255 would be assignable to create IP addresses, and we know all this because of the subnet mask. Okay, hopefully this will become more clear as we go further along. Okay, so about the subnet mask itself, you'll notice that they tend to not have a wide variety of numbers in a subnet mask if you're looking at it. And that's because you can only construct a subnet mask in certain ways, and that is with a series of uninterrupted ones. So this over here in green on this row, this is a valid example of a subnet mask. There's no zeros in there before it becomes all zeros. You can't intermingle them. And because of that, the math works out in certain ways where you only get certain numbers and not other numbers. If I threw a 0 in there, anyway, it would create. I'll show you on a spreadsheet in just a second. The second one, we have a 0 dropped in there. That's against the rules for a subnet mask. You can't do that. So if we took these numbers and then represented them in a decimal form, potentially they could come out to something like this. This 128 is a number that could be created by, in the third octet here, a set of, well, that is the first bit set to 1 and all the rest of them set to 0, so that's a valid number. But this last one right here, 129, you could only get that if you set the first bit and the last bit in that octet to 1, and that's not allowed. You would have a break. So let me show you what I mean here. All right, so if I set these all to 1, then 255 is a potential number. If I turn this to 0, 254 is a potential number, and that's 252 is a potential number, 248. So between 248 and 252, it's not possible to have a subnet mask that has that number. If I just randomly drop something out there, you'll never see a 232 as a subnet mask. That's not allowed. But you can see a 248 or a 240, etc. So that's how subnet masks are created. They're kind of a subset of the 0 through 255 number that you see, but it can only be created by an uninterrupted series of ones before you get to the zeros. Okay, so a little X's there says you can't do that. Okay, so one of the things that we need to know how to do is take any IP address and then take a subnet mask from it and then be able to draw a couple of conclusions from it. One is to determine what the actual network space that it's in, kind of like the floor of the building. And then later on, well, here's a couple other things you can also know and we'll need to know, but we'll just focus on the network for now. But other things you'll need to know is not only extracting the ultimate network within which an IP address is found, but later on we'll also want to know what is the broadcast address, so the upper end, the network address that we'll talk about now, which is the lower end within a particular range, and then what are the assignable hosts? So between the high end and the low end number, what are the possible number of devices we could put in a particular network? So this is all about network design. Like, how many devices do we need on a particular network? 10, 15, 25? 3 million. You can do that based on your knowledge of these principles. All right, so let's start off here. We have a series, we have an IP address, and then down here we have a subnet mask underneath it. Now our subnet mask is a series of uninterrupted ones, unlike our IP address, which can have something interspersed. Wherever those ones stop, so draw an imaginary line, the stuff to the left is the network address. So if we go up to here, the stuff to the left is the network address, and the stuff to the right is going to be assignable hosts. So as I come down here and with that imaginary line, and I do something called a logical AND, so meaning I'm just copying down every single number from this first address down to here, and then making everything after that last one zeros. This is the network ID. This is essentially the floor or the lower end of the network within which this IP address will be found. If I were to set these all to 1, that would be the upper end, in which in this case it would be a 255. Okay, now we still need to know how many, generally speaking, I guess you could do it manually if we, 64 to 255 and what's in between. We could figure out the number of hosts, assignable hosts that way, but that's actually not the most effective way to do it because we'll get a lot of different types of problems. So I'm going to get to that in a second. Okay, let's talk about a little bit more about classes of addresses. Up till now, I've only shown you the first 3 columns with a particular network range associated with the class. By default, it's assumed that if you so you might notice this. If you start filling in a lot of different computers, if you type in an address in the first row that fits a particular class, it's automatically going to fill in the subnet mask for you. It's assumed that if you enter in an address that's for the first number that's between 0 and 126, that the associated subnet mask is going to be 255.0.0.0. And another way of looking at this is if you select an address in the 1 to 26 range, if it starts with that number, it's assumed that the first octet is the network, identifies the network, and the last 3 octets are able to be assigned as unique numbers. So this could be like 12, 15, 222, or they could be assigned as a unique number to the hosts within that network space. If you pick a network that starts with these numbers, then it's assumed that this is the network mask. And so roughly half of your bits associated with defining the network ID, and 16 bits are associated as possible combinations for making unique IP addresses. And then lastly, if you start with 192 to 223, it's assumed that this is your subnet mask, which means that the first 3 digits are associated with your network, and the last 8 bits, or the last decimal number, is something between 0 and 255, which can be used to set unique IP addresses within that address space. So in sum, there's a lot more combinations available by default in Class C address spaces than in a lot less than in C than in B or in A. Okay, so we've talked about all these principles then. Let's kind of dig a little bit deeper now and find out, like, how can we determine the number of hosts that we can put on a network? Well, we've worked with binary math a little bit before. So over here on the right-hand side, this is where a different way of representing how, for a particular series of 8 bits, what are the numbers associated with any column number. We're not concerned with that just now, but we are concerned with combinations. So depending on the number of bits that are available for assigning to hosts, if we take 2 to that number, we get a number of combinations that are possible. So imagine that we had, for example, 8 bits available in a Class C address range, and we go 2 to the 8th. So right here, if we have 8 bits available on a particular IP address, so right here, how many combinations are possible in position Z? That's what we're answering. Or in this case, if we have 16 bits, or if we have 24 bits, how many hosts assignable are possible? How many different IP addresses can we make within that particular network? So that's what we're playing with here. So a Class C network with the last 8 bits being available, we can go 2 to the 8th. There are 256 combinations available if we have 8 bits assignable to hosts. And that's almost what we need. But we take 2 away from every potential combination so that we can assign one IP address as the network. So it has a network name, kind of like saying 40th floor or something like that. We need to have something that defines the network. And on the upper end, we need a broadcast address. So from time to time, in any particular network, we need one device to be able to talk to every other device that's out there. And we call that the broadcast address. So if we take away 2 from any potential combination, then that is the number of hosts that are available, or the number of unique IP addresses we can create in that particular network. All right, so playing with that idea, so this says, given that a Class C address uses the first 3 octets to define the network and the last octet, so 8 bits, to define a host ID, how many hosts can there be in a Class C network? So pause and try and work through the math. Okay, it's 254, and I left the reason why. So if we were only able to use the last number in the series of 4 numbers to assign as IP addresses to a network, we have basically 2 to the 8, 2 to the 8th power, which is 256 possible combinations, possible addresses we might say, but we have to subtract 2 addresses, one where we have all zeros associated with it, that's the network address, and one with all ones, and that's the broadcast address. And so that gives us 254 valid addresses. Okay, now based on that, work through this. In Class A, Class B, and Class C, in those addresses spaces, based on the number of based on the number of combinations that are possible for the hosts that are assignable, the number of bits that are associated with that particular address that are assignable, how many hosts should you be able to assign in that network? So do the math on that, and I'll move on to the next slide in just a second. Okay, so if you did 2 to the power of 24, you would get 16,777,216. Take away 2, and that's how many different devices you could assign on your network. If you use one of the 172 addresses, then you could have 2 to the power of 16, which is 2 more than this. We took away 2 for our network address, and for our broadcast address, that's the number of devices we could assign within that address space. And if we have a Class C address space, then we could have 256 combinations. 2 to the power of 8 minus 2 is 254. And here's a thought question. Why would you ever need more than 16 million devices all broadcasting to one another at once? Well, hopefully as you thought about that, there isn't really a good reason, which is why we have subnetting, so that we can divide up our networks. And we're going to use some different material to explain further how we can break up our network. So here's a quick little summary of some of the topics that we talked about, and that's it for now.